Hello and welcome back. The previous lectures we looked at using ideal gas equation of state for calculating various changes in properties across a process. Then we have used thermodynamic diagrams to be able to calculate these changes. In today's lecture we're going to look at what are known as thermodynamic tables, and following it up we'll talk about using a cubic equation of state or other equations of state for non-ideal gases, and how we can use these approaches to calculate the property changes. To begin with, let's quickly summarize what we have done so far. We defined a variety of thermodynamic properties: enthalpy, Helmholtz free energy, Gibbs free energy, how these changes are dependent on one another, and the derivatives or partial derivatives for these variables in terms of other thermodynamic quantities. And then we derived some very important relations known as Maxwell's relations that relate things that we can measure to things that we cannot directly measure laboratory setting. These type of equations will help us extract information we need from the information we can measure in the lab. Then we looked at how we can use these equations for liquids in terms of the isothermal compressibility and volume expansivity beta and kappa. And finally, we looked at thermodynamic diagrams and how these diagrams have a wealth of information in them, including entropy, molar volume or specific volume, density, the two-phase region, below the dome represented in this region, etc. What we'll do today is look at what are known as thermodynamic tables first. The information that is stored in thermodynamic tables is similar to what is given in form of thermodynamic diagrams. One of the more popular thermodynamic tables is what are known as steam tables. This is of course for water, right? There are two types of steam tables, one corresponding to what is known as the saturated steam, indicating that we have both liquid and vapor phases coexisting with one another at equilibrium. And then thermodynamic properties such as internal energy, enthalpy, entropy, density or volume, etc. are listed for saturated steam. Because it is saturated, there are two phases, one component, so there is only 1 degree of freedom, which indicates I just need to pick one property, be it enthalpy, be it entropy or pressure or temperature, whatever it is. I pick one property and the state of the system is going to be fixed. So for example, if I say that I have saturated steam with an internal energy of the vapor phase being 2455.9, which corresponds to this quantity here, 2455.9, then there is only one condition at which that happens. The corresponding temperature is going to be 60 degrees centigrade. The pressure at this condition is going to be 0.199 bar, which also means that the vapor pressure at 60 is 0.199 bar. The densities of the liquid and vapor phases are given. For the liquid phase, it is 983.2 meter cube per kg. For the vapor phase, it is 0.13 meter cube per kg. The entropy of the liquid and vapor are given, etc. So because this is saturated steam table, at each condition we're going to have there are two phases, which means all thermodynamic properties in these two, or most of the thermodynamic properties, we'll come back to that later. Most of the thermodynamic properties in these two phases are different. It has different internal energy, it has different enthalpy, it has different entropy, etc. If there happens to be a condition which falls in between the two values listed in this table, for example, if I need something at 81 degrees centigrade that falls between 80 and 82, we can simply interpolate suitably between the two conditions, do an interpolation, and then get the quantities we need. So these tables in that sense usually are closely spaced, and if there is a requirement for information in between the two data points in this table, we can always interpolate and get what we need. So again, saturated steam table, There is one for the liquid phase, one property listed for the liquid phase, and one property listed for the vapor or the gaseous phase. So internal energy, there is liquid internal energy and vapor internal energy, liquid enthalpy and vapor enthalpy. And incidentally, this difference between the liquid and vapor enthalpies corresponds to the heat of vaporization at that condition. So for example, at 70 degrees, or let's pick 100 degrees centigrade, that's the more popular one. At 100 degrees centigrade, right, the pressure is 1.014 bar. So the vapor pressure at 100 degrees centigrade is 1.014 bar. The temperature, of course, was 100 degrees centigrade. The enthalpy of the vapor is 2675.6. The units are kilojoule per kg. And the enthalpy of the liquid, the enthalpy of the vapor, we're using a subscript G for the gaseous state. And for the fluid, we're using L in this table. So let's stick with that. These are the specific values, and the enthalpy of the liquid is 419.1 kilojoule per kg. The difference between these quantities is going to be the enthalpy of vaporization at 100 degrees centigrade, or 1.014 bar, whatever it is you want to express it as. It's going to be 2615.7 minus 419.1, which is 5, 2, and 2, 2256.5 kilojoule per kg. So 2256.5 kilojoule per kg is the enthalpy of vaporization at this condition. Similarly, I can calculate the internal energy of vaporization or entropy change due to vaporization, etc. at the same condition. So this is how we can use the saturated steam table, similar to the thermodynamic diagram. I don't have to read it off the plot. I can use the table directly and get the values I want, right? And then we have what are known as superheated steam tables. This corresponds to the superheated condition, right? So there is only one phase. So the degrees of freedom is one component, one phase, plus 2. So that's going to be 2 degrees of freedom. So I need to fix 2 variables. Let's say at 8 bar, and I fix the temperature to be 400 degrees centigrade, then other values are given to me, V, U, H, and S. And similarly, at 8 bar and 800 degrees centigrade, the values are given to me, etc. Right? As the temperature increases, of course, the entropy is going to increase. The enthalpy increases, the pressure is same, but the temperature goes from 400 to 800, U, H, S, etc. increase, right? So I need now 2 variables to fix the state of the system, unlike in the saturated case where I just needed 1 variable. Once these 2 variables are fixed, I can read other quantities off the table, and we usually have a long list or a lengthy table at different closely spaced pressures, say at 8 bar, then at 10 bar, then at 12 bar, etc. And then the temperatures being 200, 250, 300, 400, etc. And again, as in the previous case, if I need something in between, I need to do an interpolation. If I need it at 9 bar, then I take the table at 8 bar and I take the table at 10 bar. And then if I need it at 9 bar and 250 degrees centigrade, I take these 2 tables and then interpolate between these 2 pressures at 250, and I'm home free. Otherwise, if I need it at 9 bar and say 225 degrees centigrade, then I first need to do an interpolation for 9 bar and 200 degrees centigrade. And then I do an interpolation between the tables at 8 bar and 10 bar, again for 9 bar at 250 degrees centigrade, right? So first I do this for 9 bar 200, then I do this for 9 bar 250, and then I take these 2 quantities and interpolate again for 9 bar and 225 degrees centigrade. We call this as double interpolation. The first time for 200, the second time for 250, and then we interpolate again for 225 degrees centigrade. That's how we get the value at 225. So we can suitably use these tables, interpolate, and get to the point we want. Depending on how closely these values are spaced, the accuracy is going to increase, of course. So that's how we're going to use these tables. What we'll do next is quickly solve one problem based on these tables. I have steam at 10 bar and 300 degrees centigrade. It undergoes isentropic expansion to 1 bar. The question is, what is the change in its enthalpy during this process, right? So we have steam that undergoes an expansion. The expansion is said to be isentropic, and we want to know the change in enthalpy, right? So what I have is a process, right? Steam is entering at 10 bar, and the temperature is 300 degrees centigrade, and it comes out, I don't know at what condition or at what temperature, but what I do know is it comes out at 1 bar. And what I again know is that the entropy is same. S2 is S1 because the process is isentropic. Similar to isobaric process where the pressure is same, isentropic process indicates the entropy is same. And if that be the case, then S2 is going to be equal to S1. I know P1 and T1, I know P2. Now we want to find out what the change in enthalpy is, or delta H for this process, which is H2 minus H1 is. We want to find this quantity. Let's see how we can do it using the steam tables. This is steam, right? So because I know two conditions, P1 and T1, I can go back to the steam table and look at the values for entropy and enthalpy at these conditions. So I'm going to read these two numbers off the table directly, and it turns out that at 10 bar and 300 degrees centigrade, the entropy is 7.1251 kilojoule per kg Kelvin, and H1 is 3052.1 kilojoule per kg. So we're going to read it off a superheated steam table as we have done earlier, right? Coming out, so I know what it is at the initial condition. Now the process is isentropic, right, which means S2 is going to be equal to S1, or S2 is 7.1251 kilojoule per kg Kelvin. We're coming out at 1 bar. So the first question to ask is, am I going to be in a two-phase region or am I going to be in a single-phase region at 1 bar? Because I don't know the temperature, I cannot answer the question right away. But if I look at the entropy, maybe I can. So what I'll do is I'll take 1 bar, right, and go to a saturated steam table. P2 is 1 bar. From the saturated steam table, let me look at the entropy values. For the liquid, it is 1.3027. Obviously, this value S2 is much higher than that of the liquid, so it cannot be only liquid. And for the vapor, it is 7.3598 kilojoule per kg Kelvin. So from the saturated steam table, when I look at the entropy at 1 bar, it turns out that the liquid entropy is lower than S2, the final total entropy of whatever is coming out, which in itself is lower than the vapor entropy. What this tells me is that whatever is coming out cannot be liquid, cannot be vapor. The only way this can happen is if it is in between, or if it is a mixture of both liquid and vapor, right? So whatever comes out is going to be a mixture of both liquid and vapor. Let X be the fraction of vapor. Then S2 is going to be the fraction of vapor multiplied with the vapor entropy plus the fraction of liquid, which is 1 minus X, multiplied with the liquid entropy. So then, depending on the value of X, which is obviously going to be between 0 and 1, we can always end up with the value of S2 that's in between these two numbers, which is S liquid and S vapor, which is what we have. S2 is 7.1251, which is in between S liquid, which is 1.3027, and S vapor, which is 7.3598. So my situation is I'm going to have a two-phase mixture coming out, and The fraction of the vapor in this two-phase mixture is going to be X, and we usually call this X as the quality of the steam. It's the vapor fraction in the stream. So now, since I know S2, I know S vapor, I know S liquid. S2 is right here, S liquid is here, S vapor is here. So once I know these three quantities, I can always go back and calculate X, right? So let me see. X is going to be S2 minus S liquid over S vapor minus S liquid. So that's going to be 7.1251 minus 1.3027 over S vapor is going to be 7.3598 minus S liquid is 1.3027. And if I solve for this number, it turns out to be 0.9613. So the fraction of vapor at the outlet is 0.9613. Once I have this number, I can always go back and calculate the entropy, in this case enthalpy at the outlet, which is X times H for the liquid, because I have X as the vapor fraction, it is X times H for the vapor plus 1 minus X times H for the liquid. At 1 bar, I'm going to go back to saturated steam, write down the values of H for liquid and H for vapor. The numbers I have are 417.51 and 2675.4. Once I put these two numbers back in here for calculating H2, what I get is 2588 kilojoules per kg. I already know X, right? I already know X from here. I'm going to put that value here, and then the two values of H liquid and H vapor from the saturated steam tables here. Once I do that, I can calculate H2 to be 2588 kilojoules per kg. And finally, delta H is going to be H2 minus H1. I already know H1, 2588 minus 3052.1. That will be delta H, which is going to be minus 464.1 kilojoule per kg. So the value for change in enthalpy is negative 464 kilojoule per kg. So to solve this problem, all we have done is simply use the steam table and the condition that the entropy change for the process is 0. It's an isentropic process. The moment we have the steam tables, it's pretty straightforward to solve this particular problem. Now, so far what we have looked at is using thermodynamic tables and thermodynamic diagrams or the ideal gas scenarios for calculating the property changes in a process. But then in a chemical process industry, we have millions of compounds. It is not possible to tabulate the properties for all these compounds or, draw diagrams for properties of all these compounds. In addition, we're going to make several more millions of mixtures when we combine these chemical species, which is what it is in a chemical process industry. Most of them occur as mixtures. So it's going to be challenging to be able to use these diagrams or tables in most cases. For special cases like water or a refrigerant, where we looked at the diagram R134A, it's fine. But in a chemical process industry, it's not going to be very easy to use such diagrams or tables right away. So we need to come up with a way where we can handle chemical species or millions of chemical species and their mixtures. We have looked at how to do that if it is an ideal gas-like scenario, but for other cases, we still have to find a way to do it. So the way we handle these property changes in case of non-ideal gases is introducing what are known as residual properties. In some books, you may see the usage of the word departure functions. So either one essentially means the difference between what it is in a non-ideal scenario to what it is in an ideal scenario at the same temperature and pressure conditions. We'll come back to that in a minute. But before we go there, let's quickly introduce an idea. Now, if we have a homogeneous fluid of constant composition, then we have written several relations for thermodynamic properties. One of the more important ones for a chemical process industry, as I have talked about earlier, is dG is VdP minus SdT. This is important because the change in Gibbs free energy is related to the changes in temperature and pressure on the right-hand side, which can be directly measured. So this, in that sense, is a special case which we like for our calculations. Now, I'm going to take this and try to rewrite it a little bit. Let's see if I write d of g over RT, then it's going to be dg by RT minus g by RT square dt. I'm just opening these parentheses and writing it as dg and dt, right? Now, dg itself is VdP minus SdT, so it's going to be VdP minus SdT over RT minus g by RT square dt, right? And again, I'm going to replace that g with H minus Ts. Here I've replaced dg with VdP minus SdT, and then do a little bit of simplification so that in the end, what I end up with is going to be V by RT dP minus H by RT square dt. This is going to be d of g by RT. So d of g by RT is going to be V by RT dP minus H by RT square dt, right? And remember how we have taken the partial derivatives. If I say what would be the partial derivative of g over RT with respect to P at constant temperature, it's going to be straightforward. It's going to be simply V over RT. And similarly, the partial derivative of g over RT with respect to the temperature at constant pressure is going to be, it's constant pressure, so the first term drops out and we're taking the derivative of this, and from the second term, that derivative is going to be negative H over RT square, right? So if I have G over RT as a function of temperature and pressure, then I can take the derivative with respect to pressure at constant temperature, I can get V. I can take its derivative with respect to temperature at constant pressure, I can get negative H. And then once I have V and H, I can calculate S, because S is simply H minus G by T. So it's going to be H by RT minus G by RT. This is going to be S over R. And U, because I know H, I can calculate U. U over RT is going to be H over RT minus PV over RT, and so on. So once I know G over RT as a function of temperature and pressure, then I can calculate all the thermodynamic properties. In fact, you can derive a relation for the Helmholtz free energy also. I can calculate V, H, S, U, everything. So in that sense, we are using G as a generating function for all the thermodynamic properties. We generate or calculate all the thermodynamic properties using G. So it's called as the generating function. Now, let's introduce the concept of residual properties, keeping this in mind. Residual properties. And like I said at the beginning of this section, by residual property, all we mean is the difference between the property and that in its ideal gas state. at the same temperature and pressure, right? Some properties such as enthalpy might not be dependent on pressure. Some, like volume, will be dependent on pressure for an ideal gas. But we want to take and calculate them at the same temperatures and pressures to calculate the residual property. So we're going to use the superscript R to denote the residual property. It can be for any thermodynamic property M. Mr is going to be M minus Mig, where Ig stands for the ideal gas condition. So for example, the volume or the residual volume Vr is going to be V, the actual volume, minus the ideal gas volume. So if the gas itself behaves as an ideal gas, then obviously V also will be Ig and Vr, or the residual volume, will be 0. If it is a non-ideal gas or a real gas, then of course there will be a non-zero value for the residual volume. Similarly, enthalpy Hr is going to be H minus Hij. I'm dropping the condition that all of them have to be at the same temperature and pressure. It is implied in that equation when I write Hr is H minus Hij, etc. Ur is going to be U minus Uig. Gr, or the residual Gibbs free energy, is going to be G minus Gig. Sr is going to be S minus Sig, and so on, right? Now, are these residual properties related to one another? Is Hr related to Ur, for example? Let's see. H, I know, is definitely U plus PV. And if I write it for an ideal gas, Hig is going to be Uig plus PVig, where Vig is the volume of the ideal gas. Enthalpy and internal energy are also for the ideal gases, so that equation also holds. And if I subtract one from the other, H minus Hig will be Hr. On the right hand side, it will be U minus Uig, which is obviously Ur, plus PVr. The original equation was H is U plus PV for the total property. For the residual property, Hr will be Ur plus PVr. Exact similar equation. I'm replacing everything with residual properties. And similarly, other equations follow. For example, Gr, G is H minus Ts, so Gr is going to be Hr minus Tsr, and so on, right? So this is the definition of residual property and how residual properties are related to the other thermodynamic properties. Now there is a very important idea which we are going to introduce here about the residual properties. What would be various thermodynamic residual properties at the limit of zero pressure? Limit of zero pressure is an important limit because, as we know, most gases tend to become ideal gases as we approach the zero pressure limit. So let's see what happens for each of the thermodynamic properties at this limit of P going to 0, Ur, residual internal energy. What would be this value? By definition, Ur is U minus Uig, so it's going to be P going to 0, U minus limit of P going to 0, Uig. As we approach the zero pressure limit, the volume goes to infinity. And as the volume goes to infinity, the molecules are pulled apart, so far apart that there is a decrease in their intermolecular forces when they are pulled apart, and eventually there are no intermolecular forces at very, very large molar volumes, or as V goes to infinity. And when that happens, the internal energy, which is a result of the molecular level kinetic potential and other forms of energies, because the intermolecular forces go to 0, they exactly behave as if they are an ideal gas, and U will tend to go to Uig at this limit, and so this Ur is going to go to 0, right? The temperature is same, so other types of intermolecular level energies are going to be same for ideal gas as well as for a real gas. Only thing, as you approach the zero pressure limit, the real gas, in the real gas, the intermolecular forces go to 0, and then the total internal energy will be same as that of an ideal gas, and so the residual internal energy is going to go to 0 as we approach the zero pressure limit. Now on the other hand, let us see what happens to molar volume. Limit of P going to 0, what is the value of the residual volume VR? This will be limit of P going to 0, V minus limit P going to 0, Vig. Right? V minus Vig. So this is limit of P going to 0. V in terms of compressibility factor is ZRT over P. Z is the compressibility factor. The ideal gas compressibility factor is 1, so it is simply RT by P, or this will be limit of P going to 0, Z minus 1 RT by P. Now if you observe, as P goes to 0, the gases behave as an ideal gas, so Z will go to 1. So you have a numerator which is 0 and a denominator which is 0. Z minus 1 goes to 0, P goes to 0. So both the numerator and the denominator go to 0. So that limit is indeterminate, and the only way we can determine it is going to be taking a derivative by the L'Hopital's rule, which will give us derivative of Z with respect to P at constant temperature. So this limit as P goes to 0 for residual volume is going to be determined by the slope of Z versus P curve at constant temperature as we approach the 0 pressure. So it is finite, but then it doesn't have to be 0. Now what happens for HR? HR is obviously UR plus PVR. Okay, so what happens to the residual enthalpy HR as we go to 0 pressure limit? Limit P going to 0 HR is going to be limit P going to 0 UR plus limit P going to 0 PVR. VR is finite, so PVR also will go to 0, so HR in that sense will go to 0. What happens to GR? Derivative of GR over RT with respect to T at constant pressure we said is minus HR by RT square. So, and HR is 0, so this derivative is 0 at the limit of 0 pressure, limit P going to 0, derivative of GR over RT with respect to temperature at constant pressure is 0, which implies GR over RT is a constant, independent of temperature. Right? At the limit of 0 pressure, GR over RT is a constant, independent of temperature, because the derivative with respect to T goes to 0, and so on. So what we have done is looked at the limits at the 0 pressure, limit P going to 0, UR, the residual internal energy and the residual enthalpies are 0, limit of P going to 0, the residual volume is derivative, or rather it is RT dou Z over dou P at constant temperature, and limit of P going to 0, GR is some constant, independent of temperature. Now how does this information help me? So for example, we want to calculate the residual enthalpy at some condition. How do I do this using this information? So now I have some idea about what happens to various residual properties at the 0 pressure limit. Let's see how I can use this information and calculate residual properties at other conditions. We start with G R over RT as the generating function. Remember, we have used generating function idea earlier. So we're going to use GR over RT as the generating function and try to derive all the thermodynamic properties based on this idea. So first, let me write what dGr by RT is. It is VR by RT dP minus HR by RT square dt. right? At constant temperature, this equation simply reduces to dGr over RT is VR by RT dP. So let me take the equation at constant temperature and let's see what happens if I integrate this equation. Integral going from 0 pressure to pressure P d of GR over RT is going to be equal to integral going from 0 to P VR by RT dP. Right? Now, I'm going to make a few notes on the other side. V is, in terms of compressibility factor, it is ZRT over P. VIG is RT over P. So VR is Z minus 1 RT over P, or VR over RT is Z minus 1 by P, right? So then this equation becomes integral 0 to P Z minus 1 by P dP. Or in other words, GR by RT at any given temperature and pressure, at a temperature T and pressure P, is going to be some constant J plus integral 0 to P Z minus 1 by P dP. Noting that this constant J needs to be independent of temperature. That's what we said. At the 0 pressure limit, it is independent of temperature. So J, this constant J, is independent of temperature, and GR by RT is J plus integral 0 to P Z minus 1 by P dP. So I have how GR by RT changes with both temperature and pressure. So I can take this information, take the derivative with respect to temperature, get enthalpy, etc., because I'm going to use it as the generating function. So for example, HR by RT square is the derivative of GR by RT with respect to temperature at constant pressure. So it will be derivative of J plus integral 0 to P Z minus 1 by P dP with respect to temperature at constant pressure. Remember, J is a constant independent of temperature, so that first derivative will go to 0, so that this becomes integral 0 to P dou Z over dou T at constant P dP over P. That will be negative HR by RT square. Right. Remember, earlier I have GR by RT was some constant J plus integral 0 to P Z minus 1 by P dP. I have HR. VR by RT is anyway simply Z minus 1 by P. VR by RT is simply Z minus 1 by P. So it is this quantity right here. If I divide everything with RT, SR over RT is going to be HR. Let's not do that. Let's just write them as they are. Then SR is going to be negative RT integral 0 to P derivative of Z with respect to T P dP by P minus JR minus R times integral 0 to P Z minus 1 by P dP. So I can write SR also in terms of the compressibility factor. And finally, in most cases, what I'm interested in is not the absolute value, it is the change in the thermodynamic properties, delta H, delta G, delta V, delta S, etc. And in such cases, especially for delta G and delta S, and for such cases, it is really material what this value of J is going to be. Irrespective of what value I take, it's going to get cancelled when I take the difference because it is independent of temperature. And because of that reason, it's convenient to choose J to be 0 and completely drop this term because it doesn't appear in the differences. And that being the case, we are completely off that constant and all the thermodynamic quantities can be expressed only in terms, or the residual properties of thermodynamic quantities can be expressed only in terms of the compressibility factors and how they change with temperature and pressure, their integrals, derivatives, etc. We know how to calculate the residual property, but for process calculations, the total property we are interested in, how do we transfer this information of residual property into the total property? Well, that's pretty straightforward. Since we know H is Hij plus Hr, the change in property delta H is going to be delta Hij plus delta Hr. So delta Hij is very simple. It's simply integral Cp Ig dt. I can express it as an integral of the specific heat capacity, or with respect to temperature, plus delta Hr, and Hr is something which we have written earlier. It is minus RT square integral 0 to P dou Z by dou T at constant P dP. So I can calculate, use this equation, calculate Hr at condition 1, calculate Hr at condition 2, take the difference, that will give me delta Hr, and then I can calculate the total delta H. So to be able to do this calculation, then all I need is the specific heat capacity in an ideal gas-like case, Cpig, and how the compressibility factor, which can be calculated from PVT relationship, changes with respect to temperature, or the derivative of that. Once I have these two pieces of information, I can calculate H straight away, right? Similarly, if I want to calculate delta S, the change in entropy, delta S, it is simply delta S for the ideal gas-like case plus delta S of the residual properties. So delta SR is SR at condition 1 or condition 2 minus SR at condition 1, right? And we have said that SR, we're going to write it as minus T integral 0 to P derivative of Z with respect to T dP by P minus integral 0 to P Z minus 1 dP by P. We're going to write SR like this, and SIG is simply integral T1 to T2 Cpig by T dt minus R ln P2 by P1. So again, all I need to calculate delta S is this information for Cpig and how these derivatives change, or how Z changes as a function of temperature and pressure. Once I have that pieces of information with me, I can calculate delta S for any process. Similarly, other properties such as delta U and delta G, delta A, etc. can also be calculated. So once I have HR, GR, and VR, if I want to calculate SR, it's pretty straightforward. SR is going to be HR minus GR over T, right? Since G is H minus TS, S is H minus G by T.